everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today in this video, I'm going to discuss about questions related to dielectric and magnetic materials. So first we are going to start with short answer questions. So in this first question is explain different types of solid dielectric materials and their polarization process. So when we talk about different polarization process, actually there are four types of polarization process. First one, here when we talk here, first process is electronic polarization, and then we have second process which is ionic polarization, and coming to third process, dipolar, or it is also called as orientation polarization. And then last one, whose contribution is very less, it is called as space charge polarization. And this electronic polarization, it occurs in elemental dielectrics. So it occurs in elemental dielectrics, and these dielectrics, they consist of monoatomic molecules. And we can take example as a diamond. So we have a diamond, or we can also take a silicon, germanium, which is made up of monoatoms. And then we have our ionic polarization. It occurs in ionic dielectrics. So where molecules are formed by ionic bond, like alkali halide sodium chloride, potassium chloride, or sodium bromide. Then orientation polarization, it occurs in polar dielectrics. Here when we talk about polar dielectrics, we have hydrogen chloride, or we can also take water, where here hydrogen bond will be present, and in this each molecule, without any application of external electric field, one atom it will act as positive end of diode, and other atom it will act as negative end of diode. And this space charge polarization, generally it occurs in alloys, where we are combining different elements and non-elements, and where we have formation of interfaces. So these are the different polarizations occurring in different dielectric materials. Next is write Lorentz relation for internal field or local field. So when we take local field, or it can also be represented as EI, and it is given as E plus P by 3 epsilon naught. So this is the relation. E's are applied electric field, P is polarization vector, and epsilon naught is permittivity of free space. Now, how ferroelectric material is different from normal dielectric material? So if we take normal dielectric material, and when we insert it between two capacitor plates, and when we apply electric field, then generally these plates, they become, of course, first these plates, they'll become charged, and within dielectric material, polarization process starts. What is polarization? Where we have separation of positive and negative charges. So dipole formation takes place throughout the dielectric material. This is the case of normal dielectric. But when we take ferroelectric material, what we are going to observe here is, generally we are going to apply AC electric field. So here alternating electric field, and of course here electric field is applied. And first polarization, when we talk about this polarization process, it is going to follow hysteresis curve. And in this hysteresis curve, actually we'll take electric field on x-axis and polarization on y-axis. And here, even though once we take out our electric field back to zero, there is some polarization retained by ferroelectric material. That polarization, it is called as remnant polarization or retentivity. And because of this retention of polarization, it is used in memories. And one more thing what we have to understand here is, these ferroelectric materials, so after removal of electric field, they are going to maintain spontaneous polarization. So that is the difference between normal dielectric and ferroelectric material. Now write Clausius-Massotti equation. So coming to Clausius-Massotti equation, epsilon r minus 1 divided by epsilon r plus 2 is equal to n alpha by 3 epsilon naught. So this is the equation for Clausius-Massotti equation. Now name different types of polarization. Already I told you there are 4 types of polarization. And what is the phenomena of polarization, that also we have discussed just now. And then what is the difference between local electric field and applied electric field? So applied electric field, of course, it is the field applied in order to undergo polarization inside dielectric material. But when we talk about local electric field is what is the electric field at an atom which is selected inside the dielectric material. Okay, so here we are trying to make out, because of polarization process, if we consider one point or an atom inside the dielectric material, then if we try to find what is the electric field because of polarization at this particular point, then we are going to observe that it is made up of this local electric field. It is made up of combination of microscopic fields and macroscopic fields. And when we talk about macroscopic fields, so here if you take your internal field or local field, as I told you, it is combination of macro plus microscopic fields. And when we talk about macroscopic, here we talk about field generated because of charges on the capacitor plates and because of charges on the plane surfaces of dielectric, which are denoted as E naught plus EP. Whereas when we talk micro, where we are talking about smaller dimension, so for that, what we are going to do around this atom, we are going to assume a sphere, and on the surface of this sphere also, polarized charges will develop, and that electric field due to polarized charges on that imagined sphere, it is taken as ES plus this sphere inside it consists of atoms or molecules which are in the mode of dipole, which are in the state of dipole, and electric field due to all such dipoles, it is taken as EM. So this combination of micro and macroscopic fields is internal field, whereas applied field is just field required to make dielectric material undergo phenomena of polarization. Then next, what are polar and non-polar molecules? So for polar and non-polar molecule, when I talk about non-polar molecule, so this is our polar molecule, this is non-polar molecule. So when we talk about non-polar molecule, here we'll say that if I consider this molecule center of gravity of positive charge and center of gravity of negative charge, they meet at same point. So for that, suppose one example I'll take, that is nothing but an atom. If I take an atom, we know that we have positively charged nucleus, and around this nucleus we have electrons revolving in various orbits. So these are the electrons revolving in various orbits, and this distribution of electrons in various orbits, it is taken as spherical electron cloud. So this is our spherical electron cloud, this is our nucleus, and if I take center of nucleus and center of this electron cloud, they are at the same point. So here positive and negative charges, they are meeting at the same point. They are not separated by a small distance. So such case it occurs in case of non-polar molecule, where molecule it is not in the state of dipole or not in the state of polarization, where their center of gravities meet. And one more thing what we have to understand here is these non-polar molecules, they have symmetrical structure, and because they are not in the state of a dipole, so dipole moment is zero within each molecule. And examples if you want to consider, we can take a H2, and here also we can have a CO2, carbon dioxide. So here N2 is also there. So these are some of the examples of non-polar molecules. Now coming to polar molecules, one best example is our hydrogen chloride molecule. And we know that this hydrogen and chlorine, they come together by sharing a single pair of electrons, but compared with hydrogen atom, this chlorine atom is highly electronegative, so it will try to pull this pair of electron towards it. As a result, hydrogen atom, it will become partially positively charged, and chlorine, it will become partially negatively charged. So here, without application of electric field, each molecule, it is in the state of a dipole, so there is dipole moment associated with each molecule. And these molecules, they have unsymmetrical structure because their center of positive charge and center of negative charge, they are separated by a small distance. So if I take one more example for polar molecule, I can take water, H2O, or we can also take ammonia, NH3. Now, write the relation between electric susceptibility and dielectric constant. So, when we talk about this susceptibility and dielectric constant, we know that susceptibility chi, it is given by P by epsilon naught E. It's the ratio of polarization to the electric field applied. And dielectric constant is permittivity of medium to the permittivity of free space. So here in this case, when we talk about this one, so chi is equal to, or otherwise epsilon r is equal to 1 plus chi. So this is the relation between dielectric constant and electric susceptibility. And then how do you account for magnetic properties of materials? So when we talk about magnetic properties, generally in magnetic materials, what we are going to observe here is each atom, it will be in the state of magnetic dipole. And why it will be in the state of magnetic dipole? Because within atom we know that electrons are revolving around the nucleus, so there will be like they will be moving around the nucleus, and when they are moving, they will be rotating about its own axis. So apart from revolution, they'll have rotation also. So we have orbital motion of electron, we have spin motion of electron, and spin motion and orbital motion, it will act as a current loop, and because of this current loop there will be generation of magnetic field, and that magnetic field direction will be opposite to the flow of current. And because of that formation of magnetic field, each atom, it will act as a dipole, and as a result, and major contribution towards the magnetism is because of spin motion. And if I take spins, when I compare electron spins of one atom to another atom, depending upon their spin alignment, their magnetic property is going to change. Next, what is Curie temperature? So Curie temperature, generally it is defined as Tc, and actually we'll say that it is the temperature at which ferromagnetic material gets converted to paramagnetic material, and it is not going to be unique for materials. So Curie temperature, it is going to be different for different temperatures, for different materials. And mention the types of magnetic materials based on their electron spins. So here we have diamagnetic materials. Here there is no spin alignment. So all spins, they are forming electron pairs. Actually, these diamagnetic materials, they have even number of electrons, and all those even number of electrons, they'll form electron pairs. So what is this electron pair? In electron pair, direction of spin of one electron is opposite to direction of spin of other electron. So there are no left out single electrons, so there is no spin alignment. And whereas when we talk about paramagnetic materials, of course we'll have single electrons, left out single electrons, but all those spins are randomly oriented, so that's why they'll show weak magnetism. Whereas when we talk about ferromagnetic materials, here all the electron spins, they are oriented along the same direction, and because of this, these ferromagnets, they are taken as strong magnets. Now, sketch neatly hysteresis loop observed in ferromagnetic material. So when we talk about hysteresis loop, generally it's a plot which is drawn between H. H is our magnetic field intensity or magnetizing field, and on y-axis we are going to take either magnetic induction, or we are going to take intensity of magnetization. And here what we are going to see here is, first when H is 0, I is also 0. As H increases, magnetization also increases, it goes to saturation magnetization. And when we reduce our H back to 0, it is going to go along this path, again it goes to negative saturation. So here it goes like this, and if it comes, so this is our hysteresis loop, this is the first path followed, and then we have this one. And coming to different terms here in this hysteresis loop, this one, it is taken as IS, this is taken as IR, and this is HC, and this one is minus HC, and this is minus IR, and of course this one is minus IS. And of course here we are applying minus magnetic field in opposite direction, and here we have magnetization, negative magnetization. And coming to these terms, IS, it is called as saturation magnetization. So it is called as saturation magnetization, and whereas IR is remnant magnetization. So it is remnant magnetization. It is also called as retentivity, and HC, it is called as coercive field or coercivity, where remnant magnetization is brought to 0. So what is hysteresis? Hysteresis is the plot which is drawn between magnetizing field and it can be magnetic induction or intensity of magnetization. And this area of hysteresis curve, it is going to represent loss associated with ferromagnetic material. And define dia, para and ferro, already I have just explained based on their electron spins. And coming to examples, diamagnet, we can take water, we can take bismuth and zinc. Here we have aluminium and copper chloride. And coming to ferro, we have iron, nickel, and of course ferrous oxide. So these are some of the examples of diapar and ferromagnetic material. And define coercivity and retentivity of a ferromagnetic material. So what is coercivity? Hc is coercivity. It is the field required to bring remnant magnetization to zero. Whereas coming to retentivity, which is also called as remnant magnetization, so it is the value of magnetization retained by a ferromagnet even when magnetic field is reduced back to zero. Now, Bohr magneton. What is Bohr magneton? It's a standard unit used for measuring magnetic moment associated with atomic system. And when I take value of Bohr magneton, it is given by EH by 4 pi m, where E is charge of electron, which is 1.6 into 10 power of minus 19. And we know Planck's constant is 6.6 into 10 power of minus 34 divided by 4 into 3.14 into what is the mass of electron? 9.1 into 10 power of minus 31. And when we substitute what is the value of Bohr's magnet, it comes out to be 9.27 into 10 to the power of minus 24 ampere meter square. And compare the relative permeability of diamagnetic, paramagnetic and ferromagnetic material. So here when I take relative permeability value, it will be less than 1. Paramagnetic value, it is mu r is slightly greater than 1. And whereas if I talk about ferromagnetic material, its relative permeability value, it is in hundreds and thousands. Then now we are going to discuss about long answer questions. Now what do you understand by dielectric materials? We have seen that dielectric materials generally they are insulators. So generally they are insulators and they don't have any free electrons. But in what way they are different from normal insulators? When we place these dielectric materials or when we apply electric field to this dielectric material, then they have this property of getting polarized. So here this will become positively polarized, this will become negatively polarized. And here within the dielectric material, we'll observe that there is separation of positive charges and negative charges. If this is the direction of electric field, then all the positive charges move in the direction of field, and all the negative charges they move in the direction opposite to field, and this phenomenon is called as polarization. Then we need to get relation between D, E and P. So for that I am going to take displacement vector. This displacement vector, it is given as epsilon E, or it is also given as epsilon naught E plus P. And coming to this epsilon E, it can be written as epsilon R, epsilon naught E, which is equal to epsilon naught E plus P. And here we can also say that from this, if I take out P common, then this epsilon naught E, it can be written as epsilon R minus 1. So of course this is the relation between D, E and P. So this relation also we can take. This is also very important relation connecting polarization, electric field and dielectric constant. And from this we can get one relation. So here P by epsilon naught E, it is taken as epsilon R minus 1. And this P by epsilon naught E is our chi. Chi is our electric susceptibility, which is epsilon R minus 1. And from this, what is our epsilon R? Epsilon R is 1 plus chi. So it is epsilon R, it is taken as 1 plus chi. So this is the relation between susceptibility and dielectric constant. Now explain in detail following terms. What is dielectric constant? So dielectric constant is the ratio of permittivity of medium to the permittivity of free space, or it is also taken as capacitance of a capacitor with dielectric to the capacitance of a capacitor without dielectric. And this dielectric constant will not have any units. Then next we have our electric susceptibility. So electric susceptibility chi, it is defined as ratio of polarization to the electric field applied. Then displacement vector, total flux density at a particular point, okay, which is placed at a certain distance. So it is called as displacement vector. And this displacement vector actually it is taken as charge per surface area. So 4 pi r square. So if I consider displacement or electric flux density about a point charge, then its formula it is given as charge per surface area. Then next, Derive relation between polarization and electric susceptibility, already we have done just now. Then explain in detail following terms. First one is polarizability. So what is polarizability? Polarizability is generally it is defined by alpha, and it is taken as a ratio, and that ratio is induced dipole moment per electric field applied. And coming to polarization vector, it is denoted by P with an arrow up, and it is defined as induced charges per unit area or induced dipole moment per unit volume of dielectric. And it has got one more definition. If suppose there are n number of atoms per unit volume of dielectric, it is taken as P is equal to n mu. Then we have electric dipole. What is electric dipole? Where two equal and opposite charges separated by a small distance. This system it is called as electric dipole. And then we have electric dipole moment. So when we have such system of two equal and opposite charges separated by distance, then dipole moment is simply product of charge into distance between charges. And here of course the unit is coulomb per coulomb meter. So here this polarization vector is farad. Here we have this is of course we have our permittivity is farad per meter, and this is induced dipole moment. So this is coulomb. Here we have coulomb meter, and here this is because we have here volume it is in meter cube. So coming to units for polarization vector, it is coulomb per meter square. And whereas when we talk about units for polarizability, it is farad meter square. So this is the unit for polarizability. Now discuss about Clausius-Mosotty equation and explain its significance. So when we talk about this Clausius-Mosotty equation, here what we have to understand here is it's the relation. It's a very important relation that will give like which is going to connect dielectric constant and polarizability. So it's using this equation we can find, suppose if dielectric constant value is given, we can find polarizability. If polarizability value is given, we can find dielectric constant. And in order to derive this, again we are going to make use of this relation between displacement vector. So we are going to make use of this P is equal to epsilon naught E epsilon r minus 1, that relation. And apart from that, we have polarization vector P to be n mu, so which can be written as mu. So if I talk in terms of polarizability, alpha is equal to mu by Ne. So this can be written as, from this mu is alpha Ei. Ei is our local field. And what is the expression for local field? It is written as E plus P by 3 epsilon naught. And then next, I'm going to make use of this relation, which is given as epsilon naught E is into epsilon r minus 1. So here this is our relation between but first we have to simplify this equation. So here P is equal to n alpha E plus n alpha P by 3 epsilon naught. And if we rearrange the terms, then what we are going to get? So if I take out P common, so it will become 1 minus n alpha by 3 epsilon naught is equal to n alpha E. And from this, so from this equation, what we are going to get is here P is equal to n alpha E by 1 minus n alpha by 3 epsilon naught. Now I'm going to make use of this relation. So here in place of P, I'll write epsilon naught. So here we have this, in place of P, we are going to write epsilon naught E into epsilon r minus 1 is equal to n alpha E by 1 minus n alpha by 3 epsilon naught. Now what we are going to do, we are going to simply rearrange the terms. So here we are going to rearrange these terms, and once we rearrange these terms, we end up having our Clausius-Mosotty equation in the end as epsilon r minus 1 by epsilon r plus 2 is equal to n alpha by 3 epsilon naught. Then next question, on application of external electric field, various polarization takes place, and we have to explain those different polarization process. So first we have electronic polarization. So what is electronic polarization? In electronic polarization, First, when we take an atom, in an atom we have positively charged nucleus which is surrounded by spherical electron cloud, and when no electric field is applied, centers of positively charged nucleus and center of this negative electron cloud, they'll meet at point. They are not in the state of dipole, but if we apply electric field in this direction, then we have displacement of electron cloud in the direction opposite to the application of electric field. Then this center of negative electron cloud, which is taken as minus ZE, and center of positive electron cloud plus ZE, they are separated by a small distance. Now each atom, it is in the state of dipole because of displacement of electron cloud. So this is displaced electron cloud. This phenomena, it is called as electronic polarization. Then coming to next polarization, which is ionic polarization. In ionic polarization, generally it occurs in alkali, that is in ionic dielectrics, where molecule is formed by ionic bonding. So for that, suppose if I take sodium chloride, so first sodium and chloride, they are attached to each other by strong ionic bond, and here of course the distance of separation will be this equilibrium spacing. But once we apply electric field, then positive sodium ion, it will move to one side, and then negative electron cloud, it will move to other side. So this is our chlorine atom, and here we can observe that this positive and negative ions, they are displaced by distance x1 and x2. Okay, and this displacement of ions on application of electric field, generally if this is our electric field direction, then positive ions, they are going to move in the direction of electric field, negative ions in the direction opposite to electric field. This is called as ionic polarization. Whereas coming to last one, which is orientation polarization. So when we talk about orientation polarization, it occurs in polar dielectrics. We know that in polar dielectrics, each molecule, it is in the state of a dipole. But when we consider their dipole moment vectors, all of them, they are randomly oriented. So they are oriented in all possible directions. So net dipole moment is 0. But once we apply electric field to such polar dielectrics, all the dipoles, they are going to get oriented along the field direction, thereby giving large dipole moment. This is about different polarization process. And then next is obtain an expression for internal field. So here already we know that internal field, as I have discussed, it is combination of microscopic and macroscopic fields. So here, so when we talk about this one, so microscopic and macroscopic fields. So here, just I'm going to draw a figure. So here we are talking about this one. So mainly, as we know that this particular, so here we are going to start the derivation of internal field, and this internal field, for this we are going to take figure of again dielectric material which is placed between two capacitor plates. So this is our dielectric material which is placed between two capacitor plates, and first we know that charges, they are going to develop on capacitor plates, and then after that we have charges being developed on plane surfaces of dielectric. Okay, and then we are selecting one point inside the dielectric material. So it can be a point or it can be an atom, and then around this atom we are going to imagine a sphere, okay, whose radius is very small compared to whole dimension of dielectric. If this is R, then on this surface of this sphere we are having again charges being developed, and then inside this sphere we are going to have dipoles. So when we talk about this internal field, it is combination of four fields. One is E naught. E naught is electric field due to charges on the capacitor plates, plus EP. This is electric field due to polarized charges on plane surfaces of dielectric. Then ES. ES is because of electric field due to polarized charges on imagined sphere. And EM is electric field due to dipoles inside the sphere. And what we are going to observe here is this E naught plus EP is nothing but externally applied field E, which is taken as macroscopic field. plus ES, and EM is 0 when we consider a non-polar molecule. So this will become 0. So we are going to get this internal field like this. Now we need to find the value of ES. So for that, just we are going to assume our imaging sphere separately. So this is our imaging sphere and this is the direction of electric field. So on this we are going to imagine one small area. Okay, that area we'll take it as dA, and this area it is making angle theta and d theta with the field direction, and this point is considered as point A. Of course, this is a point A. This is P and this is Q and this is R. In order to find electric field due to charges on this imagined sphere, first we are going to find the area of the small strip which is running on the surface of the sphere, and it will come out to be 2 pi into PQ into QR. And if I consider those triangles, so 2 pi PQ, when we talk about this PQ sine theta, so it will be R sine theta into, so this will become r theta. So it will come as 2 pi r square sine theta d theta. After that, I'll see what is the charge distribution on the surface of this sphere, and this charge it is taken as normal component of polarization into this surface area dA. Then after that, electric field due to this charge DES, it is given as, of course, dq by 4 pi epsilon naught r square. So here dq is p cos theta into dA is 2 pi r square sine theta d theta divided by 4 pi epsilon naught r square. So we are going to simplify it, and in order to find total field ES, we are going to integrate it between limits 0 to pi by 2. 0 to pi, sorry, ds. So if we do it, then our ES value comes out to be P by 3 epsilon naught. So final expression for local field will be E plus P by 3 epsilon naught. Then next question. Write notes on ferroelectricity. So ferroelectric materials, we have to say that these are dielectric materials which possess spontaneous polarization. And the spontaneous polarization of ferroelectric materials, it is going to decrease with increase of temperature. And there exists one temperature called as Curie temperature, at which ferroelectric material gets converted to paraelectric material. And these ferroelectric materials, they are going to obey Curie-Weiss law. And what is Curie-Weiss law? According to Curie-Weiss law, dielectric constant, it is given by, so here if we talk about it, C. So here C is Curie's constant, and C is equal to, so T minus Tc, where C is Curie's constant and Tc is of course Curie temperature, and it is applicable at temperatures greater than this Tc, which is Curie temperature. And then what we are going to observe here is once at Tc there is conversion of ferro to para. In para, dielectric constant is going to decrease with increase of temperature, but as long as it is in ferro state, dielectric constant is going to increase with increase in temperature. And one more thing is when we consider ferroelectric materials, they are going to exhibit hysteresis loop, which is the plot taken between electric field and polarization. And then coming to next question, what is magnetic dipole? Two equal and opposite poles separated by a small distance. Magnetic dipole moment, which is the pole strength into distance between poles, and unit will be ampere meter square. And magnetic field intensity, it is the external field in which material to be magnetized is placed, or it is the force experienced by unit north pole placed at a given point in field. And coming to magnetic induction, which is given by B, it is total number of magnetic lines of forces due to magnetizing field and due to induction property of material. And this magnetic induction, it is given by B, and its units will be Weber per meter square or Tesla, whereas magnetic field intensity is given by H and units will be ampere per meter. Then magnetic permeability mu r, it's the ratio of permeability of medium to the permeability of free space. And of course that is relative permeability, which is given by mu r, and mu r has no units. Coming to this magnetic permeability, it is taken as ratio of magnetic induction to the magnetic field intensity, and also it denotes how much extent a material allows or penetrates the magnetic lines of forces. Then intensity of magnetization, it is defined as induced magnetic moment per unit volume of dielectric. And coming to susceptibility, it is taken as ratio of intensity of magnetization to the magnetic field intensity. Then obtain the relation between magnetic susceptibility chi, and then we have intensity of magnetization I, and then magnetic field intensity H. So for that, simply we know that of course magnetic, when we talk about this permeability mu, it is given by B by H, magnetic induction to the magnetic field intensity. But when we talk about B, there is one very important relation. B, it is given as mu naught into H plus I. What is mu naught? Permeability of free space, whose value is 4 pi into 10 power of minus 7 Henry per meter. So this is divided by H, right? And mu, it can be written as product of mu naught into mu r. And here in this case, this we can write as 1 plus I by H, right? And of course here we have our mu naught, and this mu naught and this mu naught will get cancelled. And here in this case, our relative permeability is equal to 1 plus chi. Chi is magnetic susceptibility, which is the ratio of intensity of magnetization to the magnetizing field. Now here when we talk about origin of magnetic moment, one thing we have to talk about orbital motion, other one is because of spin motion. We have to say that because of orbital motion it will act as current loop, and here we know that when current flows in circular coil, magnetic field is produced, and because of it it will have magnetic moment. So magnetic moment due to orbital motion, it is given in terms of magnetic orbital quantum number ml into mu b. Mu b is Bohr's magneton. Bohr's magneton is standard unit for measuring magnetic moment associated with atomic system, and similarly spin magnetic moment is given in terms of magnetic spin quantum number into Bohr's magneton. And of course already I have discussed about Bohr's magneton, and we can represent magnetic moment associated with atoms in terms of Bohr's magneton. And then comparing dia, para and ferro, first we can say that dia, it is repelled by a magnet, para attracted, and ferro strongly attracted. And when we place all these three materials in external magnetic field, diamagnetic material, it is going to attain feeble magnetization in the direction opposite to field, para in the direction same as field, in ferro very large magnetization in the direction of field. And of course ferro is strong magnet. Already I have discussed about the spins. Diamagnet, because it has even number of electrons which are forming electron pairs, so there is no spin alignment. In paramagnet, all the spins, here what we are going to observe here is all the spins are randomly oriented. In ferro, all the spins are orderly oriented. And this diamagnets, they are going to have this susceptibility negative and small, and it is independent of temperature, whereas paramagnetic material susceptibility is small and positive, and it is inversely proportional to temperature. Whereas in ferromagnetic material, susceptibility, of course it is very large. Susceptibility is large and positive. And one more thing what we have to understand here is it is dependent on temperature in a complex manner, which is given by Curie's law. And here also there exists a Curie temperature where ferromagnet gets converted to paramagnet. And when we apply temperature, diamagnet, there exists one critical temperature at which dia gets converted to para. In para also, when we increase temperature, this para, it is going to get converted to diamagnet. Ferromagnet at temperature Curie, it is going to get converted to paramagnetic material. And one more important point is when we keep these three materials in external magnetic field, when we take diamagnet, it is going to pull out magnetic lines of forces away from center of material. Whereas this paramagnet, it is going to allow like few penetration of magnetic lines of forces, whereas ferromagnet, it goes for very high penetration of magnetic lines of forces. And here this already we have seen, B is equal to mu naught H plus M. And then BH curve already we have defined, and also we have defined retentivity as well as coercivity. So next, coming to part C questions. So first problem, here we were given value of susceptibility chi, and we were asked to find, of course we are supposed to find susceptibility. We were given value of dielectric constant. So what is the formula we are going to use here? Simply epsilon r is equal to 1 plus chi. And coming to second problem, here we were given value, but it is in centimeter square, so we have to convert it into meter square. So minus 2 whole square. So that will give us value in meter square. And we were given value of plate separation. D is equal to 1 centimeter, which is 1 into 10 power of minus 2 meters. And we were also given potential applied, and we need to find capacitance as well as charge. So here I'm going to make use of formula. Capacitance, it is given as A epsilon naught by D. So this is the value of capacitance. And once we get capacitance using this formula, what is epsilon naught? Permittivity of free space, whose value is 8.8 into 10 power of minus 12 farads. And then next, how to find charge? Charge is using formula charge per potential. So from this, charge is capacitance into potential. Potential value, it is given as 100 volts. Then coming to next problem, here we were given a gas, and its concentration is given, how many atoms are present per unit volume, and also we were given value of dielectric constant. We need to find electronic polarizability, and here formula used is alpha E is equal to epsilon naught into epsilon R minus 1 by capital N. And here epsilon naught is permeability of free space, which is 4 pi into, here this value is 8.85 into 10 power of minus 12 farad per meter. Epsilon R value is given. This is the value of epsilon R. And also we were given, this is our capital N, number of atoms per unit volume of dielectric. Then coming to next problem, here in this case reverse, we were given value of N, and also we were given value of polarizability, and we need to find value of epsilon R. So we are going to make use of same formula. And in this particular fifth problem, here we were given value of area. Area is 650 millimeter square. So it will become 650 into 10 to the power of minus 3 whole square meter square. And then we were given plate separation, which is 4 mm. So it is 4 into 10 to the power of minus 3 meters. And charge is also given, which is 2 into 10 power of minus 10 coulombs. Dielectric constant value is given, which is 3.5, and we need to find voltage. So for that, there are two formulas for capacitance. One is A epsilon by D, which is equal to, this capacitance, it is given as Q by V. Or epsilon, it is written as epsilon naught epsilon R D, which is equal to Q by V. From this, what is our potential V? So it will become Q D by A epsilon naught epsilon R. So using this formula, we are going to get solution for fifth problem. Then coming to sixth one, here we were given value of H, which is magnetic field intensity, and also we were given value of relative permeability. And we need to find B value as well as intensity of magnetization I. First, we are going to find this from relative permeability. So here we were given value of relative permeability mu R. So first we'll find value of intensity of magnetization. We know that this chi, that is magnetic susceptibility chi. So 1 plus chi is equal to mu R. And from this, what is our chi? Chi is mu R minus 1. So it is mu R minus 1. And this is 15 minus 1, which is equal to 14. But susceptibility is I by H. Now from this, what is I? I is susceptibility into H. Susceptibility we got as 14, and H value it is given as 250 ampere per meter. So we are going to get intensity of magnetization. And once we get intensity of magnetization, how we can find magnetic flux density for this? We have to make use of this formula, which is given as mu naught into H plus I. We know value of mu naught, which is permeability of free space. It is given by 4 pi into 10 power of minus 7 Henry per meter. We were given value of H, which is 250 ampere per meter, and we got value of I. If we substitute, we are going to get B value. And what is the unit of B? Tesla. And whereas coming to this problem, we were given value of magnetization, and we were given value of magnetic field intensity. We need to find relative permeability. We know that relative permeability is 1 plus magnetic susceptibility chi. And if you want to write susceptibility in terms of magnetization, it is M by H. So it will be 1 plus, what is the value of M? 3300 divided by what is the value of H? 220. So if we solve it, we are going to get value of relative permeability. Now coming to last problems, here we were given value of chi, magnetic susceptibility, which has no units, and we need to find permeability mu and relative permeability mu r. First, we'll find the relative permeability by using formula mu r is equal to 1 plus chi, which is 1 plus 2.3 into 10 power of minus 5. And after that, how we are going to find mu? Mu is simply mu naught into mu r, where mu naught is permeability of free space. Then coming to this problem, here we were given value of H and we were given value of intensity of magnetization M, which can also be denoted by I, and we need to find mu r. So mu r is equal to 1 plus chi, which is equal to 1 plus I by H. Then coming to last problem, here we were given value of H, which is 10 to the power of 4 ampere per meter. We were given value of susceptibility, which is 3.7 into 10 power of minus 3. And we need to find value of magnetization and magnetic flux density. So chi is equal to I by H. From this, how we can find intensity of magnetization? Simply product of susceptibility into magnetic field intensity, which is 3.7 into 10 power of minus 3. And what is the value of magnetic field intensity given? 10 to the power of 4. So we can get our intensity of magnetization. And of course, in order to find B, what is the formula? Mu naught into H plus I. We know mu naught. And of course, H is given, I value we have calculated. So once we get it, we can express our V in Tesla. So these are the different expected questions related to dielectric and magnetic materials. So I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.